are welcome to this lecture. Today, we are going to talk about the design and simulation of regenerator. You may remember that we have talked about different type of regenerators, and it is a fixed bed type, it is a rotary type, and out of that we have specifically looked into the fixed bed type regenerator. You may remember that we have solved some governing equation for those regenerator fixed bed type counter current regenerator. And to add to that, there are regenerator of counter current and parallel current regenerator similar to the heat exchanger, but it is not possible to have a cross flow type regenerator. So, generally we have counter current and parallel current regenerator, and here we are going to talk about the fixed bed regenerator. So, now in case of fixed bed regenerator, you may remember that we have solved this kind of regenerator problem, where we have seen that in one cycle the hot stream is flowing, in other cycle the cold stream is flowing from the opposite direction. So, that is how it is forming a counterflow regenerator. And while analyzing it, we have seen that these are the governing equations, and in that governing equations we have also talked about the boundary conditions, but we have said that we will not solve it, it is beyond the scope of this class. And if anyone is interested specifically, he or she can look into the Arkesha's book or this particular reference, or he can also or she can also look into the Ackerman's book for the solution of these equations. Rather, we will try to later on utilize the solutions of these equations, and while solving this equation, we will find that there are different kind of dimensionless parameters, and here we will find that there are particularly two type of dimensionless parameter. One is the reduced length, another is the reduced time. Here this is called the reduced length parameter, and this is the reduced time parameter, and this you can correlate it with the NTU, but basically this is called the lambda and pi, and this has been done by Hausen, and this analysis particularly is known as what is called the lambda pi method, and the other method is proposed by London and Coppage and London, and this is pretty similar to the heat exchanger analysis that we are familiar with, and this is called the epsilon NTU approach of solving the counter current regenerator, which is fixed bed type. So, we have chosen in this analysis or in this class to look into this particular epsilon NTU method, where we are familiar with the terms the epsilon, the heat regenerator effectiveness, and the NTU is the regenerator NTU. So, we will look into the details of this definition of the epsilon and NTU, and since we are bit familiar with this terminologies, we will go into the analysis by epsilon NTU, and we will try to later on simulate and design the fixed bed counterflow type regenerator by taking this approach called the epsilon NTU. So, now if you remember the definition of NTU, where we have NTU is defined by UA by C mean, where UA is the overall conductance and C mean is the minimum capacity fluid. In case of a regenerator, we have seen that in one cycle the hot fluid is flowing through the regenerator bed, in the other cycle the cold fluid is flowing through the bed, and the one of the fluid, whether it is the cold or the hot fluid, becomes a minimum capacity fluid, and it may be also possible that both of them are the same, or C min or C max are equal. In that case, we will have C r equals to 1. So, otherwise if we look into this definition of the NTU, it comprises of the hot side heat transfer area, the hot side heat transfer coefficient, and this is the cold side heat transfer coefficient and the cold side heat transfer surface area. And often you will find for a fixed bed regenerator that this AC and AH are mostly equal in case of a fixed bed type regenerator, but which is not the case in case of a rotary type regenerator, but that rotary type regenerator is not the subject that we are going to deal in this class. So, we will be mostly assuming that AC equals to AH and that is equals to AW, and so that is how the NTU of this regenerator is defined. And we also know that the other definition it is quite similar to the definition of the heat exchanger effectiveness, where we find that it is epsilon is equals to Q dot by Q dot max. So, the maximum heat transfer that is possible, and here in this case this will be C minimum multiplied by the maximum difference in temperature. So, this can be I mean correlated like this, that in the regenerator, when the hot fluid stream entering, this is entering at a temperature of TH1, and as time passes this TH2, this is dependent on the time, and in the later part of the cycle you will find that the cold fluid is coming at a temperature of TCI, and it is coming out at TC2, and it is dependent on time. As time passes, this is changing. As time passes, this hot fluid will be changing. So, what is fixed is TH1 and this is fixed at TC1. So, TC1 and TC2 are the maximum difference in temperature multiplied by the minimum capacity fluid, and this is Q dot is the amount of exact or actual heat that is getting transferred in the regenerator. So, that is how we define the regenerator effectiveness, and it is pretty similar to the definition of the heat exchanger effectiveness. Here what we find is the Q dot, and Q dot is defined as the heat capacity of the hot fluid multiplied by this hot fluid inlet and hot fluid outlet, but this is the average outlet temperature of the hot fluid. Similarly, in case of a cold fluid, if it is a minimum capacity fluid, we will take here the CC as the minimum capacity fluid, and in that case we have to define this is the average exit temperature of the cold fluid, whereas TC1 is the entry temperature of the cold fluid. So, this is how we define the hot and cold average temperatures. Here is the formula for the hot and cold fluid exit temperatures. Here you can see that TH2 is averaged over the hot cycle duration, and TC2 is averaged over the cold cycle duration, and this is how the THO and TCO are changing. But we are not going into the details of this temperature profile as we have said, but we will be using the final outcome of these expressions, and we will see how we can utilize this one. So, now if we look into this epsilon NTU method, we have other parameters like CR, as we have said that it is ratio between the C min and C max, and in addition to that we have another parameter in this case, which is called the matrix heat capacity ratio. So, this is a ratio. You can understand that MSCS, basically that MSCS is a product of the mass of the regenerator matrix multiplied by the specific heat of the regenerator matrix, and you have the C mean, the minimum capacity fluid, multiplied by P 0. P 0 is the total time period, it comprising of both the hot and cold fluid time period. So, this is the pH plus Pc, that is equals to P 0. Now, with this number of different type of dimensionless and dimensional parameters, if we look into the solution, it has been proposed by the Coppage and London, and they have obtained solution in terms of the number of heat transfer units and the matrix capacity rate ratio, that is Cm. Here we find that this has been given as in terms of NTU and matrix capacity rate ratio. So, these are the different epsilon values corresponding to different NTU and different matrix capacity rate ratio. So, if we know the Cm and if we know the NTU, we would be able to find out the epsilon or the effectiveness of the regenerator. Now, say imagine that if the matrix capacity rate ratio is 3 and the NTU is somewhere at 50, then we will have something like 0.975 as a regenerator effectiveness. So, this corresponds to this one and this corresponds to this value. So, this is what is the effectiveness, or the regenerator effectiveness is 0.975 corresponding to a value of NTU equals to 50 and Cm equals to 3. Now, this particular solution has been obtained for Cr equals to 1 when the regenerator is in balanced condition, or C min by C max is equals to 1. So, we will try to understand how best we can utilize this chart for designing and simulating the regenerators. So, in the next slide we are going to see we are going to talk about the regenerator simulation. Here we will find that we have what are the parameters known? NTU is known. You may remember that when we talk about the simulation, that means the regenerator matrix, all the internal things are known, its geometry is known and its inlet temperature is known, inlet temperature of the hot fluid is known, inlet temperature of the cold fluid is also known. So, Tc1, Th1, these are known, geometry and all other details like heat transfer surface area, then the heat transfer coefficient can also be obtained because we know the hot fluid flow rate and cold fluid flow rate. So, from there we would be able to calculate the heat transfer coefficient, and since the geometry is known, we also know the heat transfer surface area. So, accordingly we would be able to calculate the NTU. Please mind that we are looking for a similar, we are trying to find out the epsilon or the simulation problem for a balanced condition when Cr equals to 1. Now, here the geometry being known, we know the mass of the matrix that is present, and Cs is the specific heat because we know what is the temperature of, or tentatively what is the exit temperature of the hot fluid Th1 and Tc1 being known, we know the two extremities. So, we would be able to find out what is the operating temperature of the Cs average, and C min is already known, P 0 is the period, total period, the duration of the hot and cold fluid flow rate is known, and the time is also known. Here what we are now trying to find out is the effectiveness of that particular regenerator. So, how do we do that? Here once we know the NTU and once we know the CM, we have to look in the chart what is the corresponding value corresponding to this NTU. Say imagine, as we have said earlier, that this comes out to be 50 and this comes out to be 3, and or it may be in intermediate, some intermediate value also. In that case we have to interpolate from this chart. So, if that is so, we will find that directly we get the value as 0.975 corresponding to this one and this one. Okay. So, this is how we calculate the effectiveness or simulate the performance of the regenerator when we know its geometry and we know some of the parameters of fluid flow parameters, and this is pretty similar to our heat exchanger design, where we know the inlet conditions and the heat exchanger geometry, and we try to find out what is the exit temperature. So, this is how we know the performance or the overall performance of the regenerator. Now, in this context I would like to mention that if we are looking for a high regenerator value effectiveness value, we not only need a high NTU value, we also need to have a high value of the matrix capacity rate ratio. So, that means we need a high value of this CM, and we also need a high value of this NTU. Now, in order to get a high value of the CM or the matrix capacity rate ratio, you can understand that we should have a large mass of the matrix. We should also have a large value of the CS. C mean is basically the process dependent, we do not have much control on that, and P 0 is again the time period, it comprises of the hot and cold fluid time period. So, here this P 0 should ideally be smaller. Okay. Now, if we if it is there in our control, the mass of the regenerator matrix, obviously this larger mass will give a better value. We can put lot of mass, but obviously lot of mass will also ensure lot of pressure drop, but this CS is something where we do not have much control. CS is the specific heat of the solid, and that is temperature dependent. So, when it is temperature dependent, particularly if we have to design a regenerator for cryogenic application or low temperature application, you will find that the specific heat of the regenerator is changing very fast with the temperature. When the temperature is less than theta d by 12, you will find that the CV or the specific heat at constant volume or its constant volume and constant pressure, it is equivalent in case of solid. So, it is varying with T cube. As it is as the temperature is falling, you will find that the specific heat is falling rapidly, and it depends also on the d by temperature theta d, and some of the common material for the theta d or the common material which are used for the regenerator are chromium, copper, lead shorts, or they are porous material. So, they are having typical this kind of theta d. So, if we look into the specific heat variation of such materials, we will find that this is the typical temperature variation of the specific heat of the bronze, stainless steel and lead, and this is more or less when it is above the room temperature or near room temperature, this becomes 3 R, that is the Dulong-Petit law, but at low temperature, that is T cube law, it follows, and it falls quite rapidly. So, that means the specific heat of the material is very small, and in that case MSCS becomes very small. So, whatever whether you put a large mass or not, it becomes I mean it is a very small amount, you are multiplying with a small value of the CS, and we are losing or decreasing that particular value. So, we have to be very careful, particularly when we are designing the regenerator in this range. So, here this is lead is the appropriate material in the range 10 to 30 K, because it is having a low Debye temperature, and low Debye temperature will ensure a higher value of the Cp or the Cb and specific heat of the material. But when it is designed for higher temperature, so the stainless steel or bronze material is suitable, particularly when it is going below 10 K. All this lead or I mean so called ordinary these materials are not appropriate, and in that range we look for a special property of the magnetic material like erbium, nickel, ER3 nickel. So, these are the kind of material which are suitable for a very low temperature regenerator. So, this is what we have and other than that, if we look into the NTU part, if we have to make the NTU high, it is obvious that we should have high heat transfer coefficient for the cold side and the hot side, and then obviously you have to put more amount of surface area associated both with the cold and the hot fluid. So, with this one we will move to the design part once again. Here it is not always expected that we will have or we will encounter with a situation that CR equals to always 1. This CR earlier we have talked about this, that we have this matrix capacity rate ratio and this NTU. This chart, whole chart is meant for CR equals to 1, but we may encounter a situation where CR equals to not equals to 1. In that case, how do we make an effective use of this chart? That has been given or suggested by Keshav, and in this particular reference you can have it. And this is also I mean just to remind you that whether it is a pi lambda method or it is epsilon NTU method, Keshav has also shown that these two methods are nearly equal, and I mean they give equal results. So, it is whether you follow the epsilon NTU method or the pi lambda method, ultimate results are going to be the same. Now, in this situation when CR equals to not equals to 1, in that case if we have to make use of this particular chart, then we have to define some new parameters. One is the effective NTU and effective CME, that is the matrix capacity rate ratio we have to redefine, and this will contain this has been suggested by Keshav, that CM equivalent becomes CME, and it comprises of CM multiplied by CR divided by 1 plus CR, and effective NTU is modified by this relation. So, now you have the effective NTU and effective CME, and that is a matrix capacity rate ratio. So, now we can again use this chart and we get the value say like 0.865 or 0.85. So, these are the values, and these values are the epsilon 1. We will get this kind of regenerator effectiveness, but we know that regenerator effectiveness is not appropriate for us, because this chart is meant for CR equals to 1. Now, we are trying to use it for CR not equals to 1, and we have defined the NTU effective and NTU CM effective. So, with that value whatever CM the effectiveness we are getting, that is known as epsilon 1. So, based on that epsilon 1 we need to find out another parameter x, and that x parameter when we put in this equation we get the actual regenerator effectiveness. So, this is how we can make use of this chart suggested by Kobbage and London, and suggested modified subsequently by Arkesha to find out the effectiveness of this regenerator when the C are not equals to 1. Now, how do we design in case of a design problem, as you understand that situation will be slightly different. In this case, just we have to follow the reverse path. Here what is known is the effectiveness, because in this case we are trying to design the regenerator. Maybe we know the diameter of it, or we have to find out the length of it, or sometime it may be such that we have to find out both length, diameter and etc., and even the what are the particular type of regenerator matrix that may also be that may also be decided. We have to decide about that one, and there are different options. So, one by one we have to finalize, and there would be different type of constraints. So, as we understand that the design becomes always a multi objective or multivariable process. So, in this case imagine that we have certain parameters known. What is known is the overall effectiveness, what is known as the inlet temperature of the hot and the cold fluid, and what is the exit fluid temperature, that is also known. Average exit of both hot and cold fluid are known. So, in that case we have since epsilon is known, we can find out just as we have defined, if you remember that earlier expression. So, from there we can find out the x. Once we know the x, we can find out the epsilon 1. This is the reduced value, but we do not have any idea about say this CME, because CME contains Cm, and that Cm contains Ms Cs by m dot Cp P 0. So, this Ms Cs we do not have any idea about the amount of mass that is going to be there inside the regenerator. So, here at this point we have to make an assumption of this regenerator matrix Cm effectiveness. So, based on that now we have epsilon 1 and CME. So, if it is a 0.861 and CME if it is 2, in that case we know what is the value of the corresponding NTU. So, with that NTU we that becomes the effective NTU, and from there we have to calculate the actual NTU by this process. And once we know the actual NTU, this NTU can also be related by this relation, where now we have to, this NTU is now known, and this we can find out HW, HC and HC and HH can be obtained, and finally, we will be able to find out what is the area. So, once this area is known, we can also find out what is the amount of material involved with that regenerator, and when we know the material we get a value of the Cm. If it is a good guess, if we have made there would be the number of iterations will be small, otherwise with that value we have to go back to this step and we have to make an iterative solution. So, now with this value we will go to the next slide, and this is a typical cryogenic regenerator, where we find that alternative layers of such, this is a perforated plate and alternative such perforated plate and the stainless steel spacers. The spacers are given to arrest or reduce the axial conduction of the heat from coming from top to the bottom. So, this is a typical look of a cryogenic regenerator. This has been taken from the Baden's book of cryogenic systems. So, with this knowledge, we will now move to a small problem, where we will try to calculate the heat transfer coefficient and the pressure drop in a regenerator, where it is packed with the lead shot, and this is diameter of this lead shot is 1.6 millimeter, and they are packed inside a bed of diameter, it is given as 154 mm, and the length of this regenerator is 915 mm. The porosity is also given as 0.38, and the mass flow rate is basically m dot is 0.080 kg per second, and the gas is nitrogen gas flowing at a pressure of 2 atmosphere and at an average temperature of 200 Kelvin. So, with this information, we need to find out what is the heat transfer coefficient and what is the friction factor. So, you know that by this time that this J and F are the value from which we can calculate the overall heat, the heat transfer, individual heat transfer coefficient, and this will be linked to the pressure drop associated with this flow of gas through this packed bed. So, we will try to solve this example in the next class, and thank you for your attention.